Welcome to the pre-recorded presentation of the paper titled Thermochromic Animation during eCAADe 2021 conference. My name is Andreas Körner and I am a doctoral candidate at the Department for Experimental Architecture at the University of Innsbruck in Austria. The paper presents initial results of the research project Thermochromic Topologies, which was made possible by a grant from the County of Tyrol. It is a continuation of previous work on combining thermochromism with digital environmental simulations. Based on this, it investigates thermally informed and color-changing surface configurations for architectural elements. The research aims to digitally simulate and program the thermochromic effects on responsive reliefs. It is motivated by the desire to investigate digital design, simulation, and fabrication methods for the configuration of temperature-responsive architectural surfaces. Those can in turn help to visualize previously invisible parameters of thermal comfort. Materials that visibly change color relative to temperature are called thermochromic materials. The materials underneath are called substrates. A variety of those materials exists as coatings, dyes, and pigments. Their use in architecture has been explored but is limited due to a lack of UV resistance, and exterior applications remain challenging. Therefore, this paper investigates the role of heat transfer through elements to establish a design method for thermochromic animation. The art historian Heinrich Wölfflin argued that ornament can animate dead surfaces. The interior climate quality is quantified by the inhabitant's sensation of warmth and is stated as a degree of thermal comfort. Traditionally, this is the result of several physical parameters which are all invisible to the human eye. The hypothesis of the paper, therefore, is that thermochromic animation can be used to configure architectural surfaces to visually communicate those parameters through surface ornamentation. From this, three research questions were derived. First, how can material intelligence be used to visualize factors of thermal comfort? Second, how can thermochromic response be programmed, configured, and fabricated? And third, how can designers predict and plan such thermochromic response? The prototypes produced during the research tested the hypothesis by digitally simulating and therefore predicting the thermochromic response on intricate organic reliefs. The fabricated results match those predicted when exposed to the heat from the back. It has to be noted that this slide shows a prototype that followed the samples presented in the paper and is shown here to provide an outlook. The idea is that by specific design, the thermochromic response can be animated. The following design parameters have been identified: substrate thickness, relief depth, material type, coating thickness, exposure direction, porosity, and substrate pattern. Above a given threshold, in this case 28 degrees Celsius, the black thermochromic layer turns transparent and incrementally reveals the underlying patterns. To achieve this, a workflow that relies on three tools has been devised: digital heat transfer simulations, parametric design, and digital fabrication. The experiments were observed using infrared cameras and the results compared to photographs, the thermochromic response, and the simulation output. The three qualitative evaluation criteria of the thermochromic response were contrast, diversity, and speed. To understand the relationship between substrate material, color, and patterns, a series of scale samples were created using 3D printing and casting. The sample held by the hand in the picture, for example, is colored based on the graphic output of a heat transfer simulation. In response to the research questions, the experiments led to the following findings. Intricate surface articulations lead to a stronger thermochromic response. This includes imperfections, tool traces, paint pooling, and coating evenness. Thin and porous geometries perform better since their thermal mass is comparatively low. They also have a higher surface area. Cavities and inclusions have an impact on the thermochromic response. The trapped air insulates and impacts the heat transfer path inside the geometry. Flat backsides and reliefs perform worse than geometries that are equally intricate on both sides. To achieve thermochromic animation, the phase change from an initial cold state has to be programmed by configuring the previously mentioned parameters. This results in a series of distinct patterns. The more complex the geometry, the more idiosyncratic they are. By intelligently modulating the topology, thickness and porosity of the geometry, different patterns can be achieved at different stages of the process. Material properties have a big impact on how much a given sample heats up. Thermal mass can be used to further delay the effect or avoid a complete phase change at room temperature. Geometries that contain undercuts and cavity spaces appear most promising because they provide great design freedom and yield complex patterns. The downside is the requirement for more sophisticated fabrication techniques such as 3D printing. To conclude, a combination of digital simulations and material experiments can be used to configure the thermochromic response of architectural surfaces. Layers, cavities, and overhangs can affect thermochromic response. By this, surface articulations can visually highlight thermally invisible parameters of thermal comfort over distance. By investigating this through digital design research, the paper contributes to the fields of thermodynamic architecture and digital ornament, with the premise to create a closer interlinkage between material, geometry, color, and texture that extends the formal vocabulary to better communicate between the natural and the built environments. Finally, I want to thank everyone who supported this project by contribution, with advice, and financially. Thank you for your attention, and I'm looking forward to the discussion.